So hello everyone, I'm Junbo, and today I'm going to present PLatter on the feasibility of building scale power line backscatter. And this work is done together with Elahe, Artur, Reese, Swarun, and Anthony. So backscatter is a popular way of communication. I don't know why, okay. Backscatter is a popular way of communication, and a typical depiction of backscatter looks like this. So we have a reader which sends out some, say, RF carrier wave over the air, and then the tag modulates this carrier wave by, for example, selectively reflecting or absorbing it. And although backscatter can be both active and battery-free, for example, we see both active and passive RFID tags, they both feature a low cost and a low power consumption. And this makes them really ideal for massive sensor deployments, for example, in indoor warehouses or maybe in an industrial testbed. But at the same time, the simple hardware also leads to some limited performance. For example, limited range, like a few meters or maybe a few tenths of meters. And at the same time, it also kind of suffers from some limited data rate, like a few kbps. And more importantly, since they are wireless systems, they sometimes suffer from the non-line-of-sight challenges. So of course, we're not the first ones, to look into these challenges. And previous work tries to extend the range with, for example, robust chirp modulation, or they use multiple readers. And at the same time, people try to boost up the data rate with, say, smart concurrent transmission schemes, or they just turn to Wi-Fi backscatter. So in this work, we evaluate the feasibility of a brand new idea. And that is, can we put power lines in between the reader and the tag so that we can use this as an intermediate medium to greatly extend the range while maintaining a high data rate? So we call our work PLatter, which is power line backscatter. And the overview looks like this. So you can see that the reader is connected to the power lines, and the tag is put, for example, stuck on the wall with power lines running behind that might be several rooms away. So the reader and the tag, they are really beyond the traditional RF communication range. So such a system design naturally features a indoors and non-line-of-sight application, and also it enables building scale communication with existing infrastructure, like the power grid here. And our prototype shows up to 300 feet range and up to 4 megabits per second data rate. And we use 13 megahertz as our operating frequency for this one. So, I haven't explained how this one works end to end. So let's just dive into this by, for example, looking into a potential application that PLatter can enable. So imagine yourself as an industrial manager, and you want to improve your factory with, say, a bunch of sensors like these. And on one hand, the power outlets can be, scarce that might not always be available on the wall. So you cannot put your sensors or your sensor readers at an arbitrary place. On the other hand, the sensors can also be range limited. So sometimes if they're put at a weird position, they cannot access, the sensor reader. So of course, you might have several candidates for this scenario. PLatter says, well, we want to introduce a new solution. With a single reader plugged into the wall, we can read multiple tags that are rooms away without, with the non-line-of-sight scenarios. So specifically, the reader is going to inject the RF carrier wave into the power grid instead of, sending that over the air. And then the carrier wave is going to reach the tag, which might be several rooms away, several walls away. And then this is going to be modulated by the tag. And then it finally goes back to the reader and get decoded. But of course, this is really high level. So now we just dive into the system design part. And that is our wired wireless design. Specifically, we call this wired wireless because you can see that here, the reader is connected directly to the power line, while the tag wirelessly coupled with the power line. So to understand why this is backscatter in the first place, we look into the tag design first. And specifically, we feature a low-power design without an active radio front end at the tag. And that is to say, our tag is not, completely passive. It has a small battery, but it never actively radiates any signal. So how can you communicate without transmitting anything? And our key intuition here is that power lines are wire conductors. So you might recollect from basic physics that if you have a wire conductor and then you have a current flowing through, then you will have generally this magnetic field. And now if you put a coil nearby, they couple with each other. Quite simple, right? So as I said, we inject the carrier wave into the power line. And in this case, we are having this RF electromagnetic field. And in this project, we focus on the near field. Now, if you view this wire plus the coil as an integrity, then this coupling effect is effectively introducing some additional impedance on the wire. And we call this impedance parasitic impedance. So now, what if I let the coil toggle between two different loads? Well, if you're familiar with RFID, you know what I'm doing here. So I'm trying to introduce alternating parasitic impedance to the wire. And with this alternating pattern, we can embed some backscatter data bits. So well, these are perfect theory. Does it really work in practice? So to understand that, we did this preliminary study with the VNA. Specifically, we have a 100 feet cable, which we usually find behind the walls. And then we terminate the cable with SMA open cap. And meanwhile, we use the vector network analyzer to measure the impedance of the power line. And we put the tag 8 centimeters from the center of this cable, and then we let it toggle between two different loads. So the measurement, wow, really clear, right? So we see the 0101 bit patterns here. So this is indeed saying that, okay, our tag is trying to introduce some change to the parasitic impedance of the wire. And this is really the basis of PLatter's backscatter. And we call this parasitic impedance amplitude modulation. I mean, a fancy name, but actually it's just a variation of ASK. And further, we make this communication unidirectional from the tag to the reader just in favor of tag's simplicity. So if you see our tag here, right? Apart from the loop antenna, we have an SBDT RF switch, which toggles between two different loads. And then we have the MCU to control the switch, and then we have a small battery. But as I said, we never actively radiate signal, so that's why this tag is low power. But of course, we have more details about, like, say, channel coding of the tag, or maybe detailed calculation, so you can discover more of them in our paper. So at this moment, right, the tag is doing parasitic impedance modulation. So our reader is really simple, right? It's just measuring the impedance, and then we're done. Not really, to be honest. And there's one question remaining, and you might have asked this in your mind. And that is, how can we even guarantee that the signal can traverse or even enter the power line in the first place? And the formal name of this challenge is called impedance mismatch. But to understand this very comprehensively, we have to dive into circuits. So I'm not going to do that for today. Instead, we can just understand this problem in a very simple way by looking into these two different pictures. So these two wires, they look quite different, right? And the reason why they look quite different is because they're designed to carry signals of different frequencies. So specifically, if you try to inject some RF signal into this 60 hertz cable, generally speaking, you're going to have a huge reflection at the reader cable interface. So the signal is going to say, hey, I refuse to enter. And the reason is that the cable has a mismatched impedance with the VNA. So a general solution for this one is to insert this small piece of circuit called the impedance matching network. It tries to match the impedance of the cable with the VNA so that the signal can enter. Now, of course, this is our reader's task, so we dive into the second part, and that is our reader design. Specifically, as I said, we have to put the matching network at the reader cable interface. So in this case, this is going to be, trying to match the whole power grid with the appliances potentially running. And it sounds challenging, right? A large network to match, but it's just circuit design problem, right? So as long as the impedance of the grid remains the same, we're done. Just insert that small piece of circuit. Magically works. Well, what did I say? We need this to remain the same, which is definitely not the case. So suppose I have another light bulb, and I turn this on, right? Boom. Like the impedance just changed. And if you think of this in practice, other than you might randomly, switching on and off different appliances, even a single appliance like your refrigerator, it has multiple operation modes, which also makes this time varying. And indeed, in practice, this really has a wide range of variation. And a single matching network just won't do this thing. And that's why I introduced this module called real-time impedance tuning. And then specifically, we designed this PCB board, which has 4 channels on board. And each channel is a tunable network that can match a range of impedance. So together, it can cover a wide range of possible values that we're going to encounter in practice. And of course, we have several other essential blocks, like this notch filter, which tries to eliminate the power AC signal, like the 110-volt signal, so that we can plug in our system into the grid without burning our reader, and more importantly, not burning myself. And of course, we have other essential blocks like these, but in the interest of time, please refer to our paper for more details. And now we dive into the implementation part. And we deployed up to 300 feet power lines inside a large industrial environment. You can see the cables extending the whole area. And we did a ton of experiments on this. Specifically, we did the evaluation on static cables to study the impact of system variables shown here, like cable geometry, like separating materials. By static cables, I mean that they do not carry active power. And this is done with a single tag. Meanwhile, we have a trace-driven simulation with multiple tags. And finally, we have an end-to-end trial where we just plug the system into the active grid. And this is done by literally me here. So very dangerous, but I'm still alive. So it means that it kind of succeeded. So for today, we're going to dive into these 2 experiments. Now, the first one looked quite similar to the VNA test case. So we have 3 different candidate cable lengths, 100 feet, 200 feet, and 300 feet. And we can also vary the tag distance to the cable. And we can even vary the tag's position, like here is the beginning, the middle, and the end. So we show the SNR that the tag can enjoy at different positions. You can see that this is the figure that we get. Of course, I know that the SNR look really negative in this case. And this is because they are the raw values without taking into account the coding gains from the tag or maybe the noise removal algorithms. So in practice, we show that if we are more than minus 16.5, we are good. But of course, the higher, the better. And translating these numbers into data rates, we can get this figure. So the highest data rate we can get in this case is 4 megabits per second. But of course, if you, for example, put the tag a little bit further, then you might experience some drop. So kind of the takeaway from this experiment, the first one is that 4 megabits per second is achieved under the most ideal condition. So this actually takes into account the gains from coding and also denoising. And there's a natural trade-off between tag distance and tag position. So if you want to be farther from the reader, then generally speaking, you might to be closer to the cable. And also a trade-off between tag distance and cable length. So if you want the cable to be longer, then you might have to be closer to the cable as well. And for the active power experiment, here we have a 25 feet cable, but we plug in the whole system into the active grid. And it really has hundreds of meters of cable hidden behind the outlet. And we did nothing about this one, so the whole building was working normally. And that's why we see a lot of sudden changes, here. Like, I don't know what happened. Maybe someone was using some appliances. And other than this sudden noise, we also see a lot of leftover from the AC signal. So as I said, we have the notch filter to filter out the AC signal at 60 hertz. But again, we have all of these higher order harmonics from that one. Although they look messy, they are readily easy to filter out. So that's what we did. And then after we filter out these 2, we get a decent SNR, like -7, -6, which is well above our decoding threshold. So this is really good. And of course, at the moment, this is a feasibility study. So we acknowledge some limitations for the system. For example, currently we require the tag to be relatively close to the cables, like several tens of centimeters. And also, we see some variables that can make our performance fluctuate. And it's currently unidirectional. But I think in principle, it's feasible to make this bidirectional as well. And then with all the wonderful work on concurrent transmission, I'm sure we can scale the tag easily in the future. And I do want to acknowledge that this work is also related to power line communication. where we see people using power lines for, as transmitting antennas, as receiving antennas, as transmission lines. So we use this one to facilitate backscatter communication. So yeah, that's it for today. We see PLatter. It's a building scale backscatter communication system. So feel free to discover more details on our website, and I'm happy to take questions. Thank you.